Welcome to Foundational Concepts in Generative AI by Ash Stewart. Episode 2. What is the meaning of? No, not life. We haven't gone that far enough to be able to answer that question. Right now, the more pertinent question here, and one that's easier to answer is, how does AI, specifically how do large language models, LLMs, represent meaning? In my previous article, we touched upon the concept of a bit, a binary unit of information that simply encodes a true, false, yes, no, I do, I don't kind of message. But as we know, there is much more to reality than just I do. The next step from a simple 0 or 1 expression is, of course, bigger numbers, the basic arithmetic that we're all taught fairly early in our childhood. This in itself allows us to answer a simple question, such as, how many apples are there in that bag? Or a dandier one, such as what is the torque on the third nut on the engine of the Falcon 9 rocket at a given altitude, which can be handy if you're going to be interviewed by Elon Musk. To help visualize numbers, we can plot them on a number line. Here, of course, we are enlisting the services of geometry, which is very helpful in developing a better understanding of this and some of the other concepts we will touch upon here. For example, looking at numbers well laid out on a number line, we can instantly tell that 18 is closer to 20 than to 3 without having to carry out any calculations in the head. While this is a fairly silly example, such visualizations can be even more valuable when the data points in question are much bigger, or, as we'll see, more complex. See article for an image of a one-dimensional number line. So yes, let's dial the complexity notch up a bit. Numbers laid out on the number line represents a single dimension. What about having 2 dimensions? Harnessing the power of geometry again, we can lay out 2 perpendicular lines, the classic x and y axes, to bring up the Cartesian plane. On this, we can plot a point, say 2, 3, where the numbers x, y are on the respective x and y axes. This now represents a point on the 2-dimensional plane. Again, we can have another point on the 2D plane, say 4, 5, and assess the distance between the 2 points. And just as we did with the comparative distances between 3 numbers, we can make similar assessments of the comparative distances amongst 3 or more points on the plane, which could be of value in some contexts. See article for an image of a 2-dimensional plane. Another important point is that all of this can be translated into algebra by way of algebraic equations. And by resolving these equations, it's possible to answer, with precision, questions such as the distance between 2 points and so on. Again, this will come in handy. It's now possible to go further and visualize a 3-dimensional setup. Analogously, we have 3 axes here, x, y, and z, and as is obvious, a point here, say 3, 2, 4, represents a point in 3-dimensional space. Just as before, we can have several points in space and ponder over their relative distances from other points. And now, see article for an image of 3D space. Again, and just as importantly, it's possible to translate the representation between geometry, the visual part, and algebra, the equations part. Noting that one can go in either direction, given just the equation, plot the graph as well. That last point must be emphasized because that is what we are going to do next. Start with just the algebraic part. This is simply because we just cannot visualize a 4 or any bigger dimensional space, but it's possible to express it algebraically, and just as in the previous cases, represent it in the computer. Why would we need a 4-dimensional space at all? The answer is quite simple. In any of the above setups, the number of dimensions encodes or answers that number of questions we may ask of any given point in that space. Put simply, the distance of that point along that axis from 0. For example, the point 3, 1, 6 resides in 3D space with its distance along x, y, and z axes being 3, 1, and 6. This is a way of encoding that many pieces of information. So here's the kicker. In real life, the meaning of anything, any particular thing we wish to express, even the simplest idea, object, notion, concept, the meaning of any such thing is so complex as requiring several dimensions to represent it. So the method used to represent meaning in artificial intelligence is quite simple. Create an n-dimensional computational setup using an n-dimensional mathematical foundation, just as we considered for 1, 2, and 3 dimensions, but much more sophisticated. Well, yes, but how many dimensions? It's in the hundreds. For example, 512 dimensions. This complex, hard-to-imagine setup is what is called the semantic space. Think of these dimensions as connotations of a word. For example, the word apple has different connotations. It may be the fruit or the company Apple. So while this would sit in the same section in the dictionary, written words being simple combinations of letters and nothing more, you derive the meaning in your head because you know the word when we'll see that combination. Apple the fruit and Apple the computer reside at somewhat different points of the semantic space, because the two encode differently for fruitness, companyness, computerness, etc. This is how meaning is encoded in the context of LLMs. Remember, we discussed relative distances between 2 points in 1, 2, 3D space. Hold on to that, because it's going to come in handy in the next episode, where we will expand on how all this works in practice and how it is useful. That's it for today. See you in the next one.